Hey guys, I'm back with a new video. In the previous video, we learned about the concept of soft margin and we also discussed the limitations of maximum margin classifier. So in this video, let us continue our discussion on support vector classifier. So for maximum margin classifier, the condition for maximum margin classifier comes out to be yi m0 plus m1 xi1 plus m2 xi2 and goes on till mn xin. This is greater than or equals to capital M, and here capital M represents our margin. So we are talking about maximum margin classifier. So this condition holds true for maximum margin classifier. So this means that for all the points of both the classes, in case of maximum margin classifier, all the points should lie at a distance that is greater than or equal to the margin but not less than the margin, which is happening in this case of support vector classifier, right? But here in support vector classifier, we can have the points of both the classes within the margin as well. So within the gap of 2a, we can have the points. Now coming to support vector classifier, we maximize the soft margin. So what is soft margin in this case? So any point that is lying on the wrong side of the hyperplane and is closest to the hyperplane, the distance of that point to the hyperplane will give us the soft margin. So this is the point that is lying on the wrong side of the hyperplane and this distance is say b. So soft margin for this case is b, right? Because this point is on the wrong side of the hyperplane and is also the closest one. So the goal here is to maximize the soft margin in case of SVC. So we have our coefficients m0, m1, m2, mn, and then we have some other variables as well. So for SVC coefficients, so m0, m1 and goes on till mn, as well as some variables say epsilon1, epsilon2, epsilon3 till epsilon n. So I will explain these variables a bit later. So for the support vector classifier, the objective function is a bit different. So let me write this down. So y of I, here I represents the row of our dataset and here xi1 represents the value of the first variable in the ith row. Then this xi2 is the value of the second variable or predictor in the ith row, and so on. For support vector classifier, it is a bit different. So the objective function is yi m0 plus m1 xi1. Again, xi1 is the value of the predictor, the value of the first predictor of the ith row, and let us go till mn xin. And this should be greater than equals to capital M 1 minus epsilon I. Now this I is used to represent the index of the current row of the dataset, or you can say the first row, second row, and so on. Now this term m into 1 minus epsilon I, this is nothing but our soft margin. So let me specify it right here. This is nothing but our soft margin. Now coming to the variable epsilon I, this is called as the slack variable. So let me write this down here. So epsilon I is our slack variable. Now there is also a constraint in case of support vector classifier that summation of all the epsilons that we are taking as slack variables must be less than or equal to c. So summation from I1 to n of epsilon I should be less than or equals to c. And this is a very important condition that you should make a note of for support vector classifier. Now the question here is that what is c? Now this is the hyperparameter of support vector classifier that is used for controlling the value of these epsilons. So c is a parameter whose value will be set by us. Now let us see what this epsilon value is and how it is related to c. So let me clear up all the space and let us discuss what this epsilon value is. Now if epsilon I is 0 for some data observation, then you can say that the data observation is on the correct side of the margin. So if epsilon I is 0, so this is the case 1, then our data point is on the correct side of the margin. So if you consider this point or any of these points that are on the left side of this dotted line, for these points epsilon I is 0 because they are on the correct side of margin, unlike these two which are on the wrong side of the margin, right? Then let us talk about the second condition. If epsilon I, so this is case 2, if epsilon I is greater than 0 for some data observation, then you can say that the data observation is on the wrong side of the margin. So these 2 points, which I have marked using the orange ticks, they are on the wrong side of the margin. So for these 2 points, our epsilon I must be greater than 0, right? Next comes the condition. So first let me write this down. So data point is on the wrong side of the margin. And now let us talk about case 3. When epsilon I is greater than 1 for some data observation, then you can say that the data observation is on the wrong side of the hyperplane, or you can say the data observation suffers misclassification or on the wrong side of hyperplane. So if you see this hash point, this is on the right side of the hyperplane, so it is on the wrong side of hyperplane because it should be on the left side of the hyperplane so as to get correctly classified. And since it is on the right side, so this is a misclassification, right? So for this point, which is on the right side of the hyperplane, and it was supposed to be on the left side, is a misclassification. And for this point, epsilon I is greater than 1. So the significance of epsilon is that it tells you whether a data point is misclassified or not. And from case 1 of support vector classifier, you can see that if we put epsilon I as 0, we get the objective function of the maximum margin classifier, right? Because in case of maximum margin classifier, there is no slack. So the data point is always on the correct side of margin once you are done with the classification. Now this is the hyperparameter as I just mentioned, and it controls the number of data observations that you can misclassify. So C is allowing us to change the value of how many number of misclassifications we can have on the wrong side of the margin or on the wrong side of the hyperplane, right? So if the C is 0, then no data observations can be on the wrong side of the margin or on the wrong side of the hyperplane. They would always be on the correct side of the hyperplane. So that will be the case of maximum margin classifier, in which both the classes will be perfectly separable. So if in this case C is 0, then it reduces to the case of maximum margin classifier, right? Now if no data observation can be on the wrong side of the margin or on the wrong side of the hyperplane, that is, no observation can lie within this gap of 2a and always lie outside this gap. So if all the points lie outside this gap, then that is the case of maximum margin classifier. And this can only happen when C is 0. Now if C is greater than or equal to 0, this means that at most C data observations can be on the wrong side of the hyperplane, which is this side, right? This area. Now before wrapping up with this video, let us do a simple test to see if we understood the concept or not. Let us say this point as 1, this point as 2, this point as 3, and this point as 4. So can you tell me the epsilon value for each of these points? So you can pause the video and try this on your own and let me know about the answers in the comments section of this video. So now let us try this out. So for this point, which is marked by 1, this lies on the correct side of the margin and therefore it is the case 1. Now let us go to this point marked by 2. You can see this point is on the wrong side of the margin because it lies to the right side of this dotted line. It lies within the margin, right? So for this, case 2 holds. So epsilon I or epsilon 2 is greater than 0. Now let us talk about this third point. For this point, you can see it lies on the wrong side of the hyperplane because it lies to the right side of the hyperplane or in the area in which the other points lie, right? So for this, case 3 holds, that is epsilon 3 is greater than 1. So let me write this down here. For this point, epsilon 3 is greater than 1. And let us go to the last one, which is this asterisk point. Here you can see it lies on the correct side of the margin. So for this, epsilon 4 is 0, right? So this was all I wanted to cover about the concept of support vector machines, where we discussed about the maximum margin classifier, the limitations of it, the concept of soft margin, and then applying that concept in the support vector classifier to understand how we can separate two classes which are not perfectly separable using the concept of soft margin. So let's catch up in the next one.